Okay, welcome back to the first lecture from Module 4. And if you haven't already, go ahead and download these two data sets. The Google Sheets links you can get to just by clicking on the hyperlinks there, or you can download the Excel file from our Canvas webpage. And we want to talk about measures of relative standing in this module. And we're going to find out that there are two different ways that we can represent measures of relative standing. And the first, which is what we're going to cover in this video, is talking about percentiles. And percentiles are actually a very nice way of kind of motivating what a measure of relative standing is in the first place. So I want to go back and talk about this situation that we discussed in the introduction. We had these two athletes. They each had spectacular performances, but they were in different events. And so the question is, how do we compare, the performance of two people when they come from totally different areas? And so we gave in the introduction some examples of where we have to decide between two possibilities and we can't directly compare them. And in this video, I'm going to look at the second scenario of these job offers that you get. And so we're going to use percentiles to answer this question. So if we ask the question, which of these two job offers is better from purely a monetary point of view? And very often when you take your first job, it's just for experience. So a lot of people do choose the job that pays the most, okay? And if you go ahead and click on this website, you don't have to, but if you did, you would get a little cost of living comparison calculator here. And if you type in $60,000, you see this result for Washington, D.C. That was the salary for the Washington, D.C. job. And if you type in 50,000, which was the salary for the Daytona Beach job offer, you get the following results. And so what do these numbers mean and how do we use them to make a decision? Well, if you actually look at the distribution of incomes in Daytona Beach, you can see that they're nice and right skewed here, okay? And you find 50,000. We find that $50,000 is the 44th percentile for the incomes in Daytona Beach. And what that means is if you added up all of these percentages, and so someone made a histogram here using relative frequencies, you would find out that 44% of the people in Daytona Beach made less than $50,000. And so this is what a percentile is. The percentile of a value tells you what percentage of values in that data set or in that population are less than it. Now, if we look at the income distribution in Seattle, and we see something very interesting about Seattle. Seattle does not have a right skewed distribution. And that's because there are a lot of very wealthy people. You have the Bill Gates and everything, living in that area. So we see just the opposite. It's almost left skewed. Very unusual. But in any case, if we find $60,000 and we added up the percentages of all those bars below, we would find out that 34% of the population makes less than 60K. And so we would say that 60,000 is the 34th percentile for household incomes in Seattle. Now we can easily determine which job offer is better based on just the salary. Because we see that what really matters is not the absolute value of the variable. Okay, obviously 60,000 is greater than 50,000. But what matters is where that value stands relative to the rest of the population. And we can clearly see that the Daytona Beach job offer is going to be better because your income stands above 44% of the population, meaning you have more spending power. You're actually getting close to the 50th percentile. Whereas in Seattle, you're close to the lower third, which means 2/3 of the people can spend more money than you do. And it also means that the prices are going to be, set relatively higher to you. You're going to have less spending power because the prices are set relative to this population. And so we see that percentiles are one measure of relative standing. And this is what we're going to be working with and understanding and being able to work with doing computations the rest of this lecture. So the first thing we want to do is we want to learn, how do we compute percentiles given a data set? And if you go ahead and open up the data set on the Major League Baseball salaries, we're going to compute the 90th percentile in that data set. And so we're going to do that by using summary stats, and it's going to set up the same sort of way that we did when we computed the mean and the median and those summary statistics. We'll go to stat, summary stat, column. It'll bring up that same window. Again, you're going to click on the variable that you want to analyze, which is salary. And then down here, you're going to type in the percentile. And so if I want the 90th percentile, I'm going to type in 90 as in 90%, not 0.9. And when you do, you find out that $1 million is the 90th percentile. So let me run through that with you in StatCrunch just to show you how that works. So here's my salaries. And I'm going to go to summary stats, columns. I want to analyze salaries, and I want the data value for the 90th percentile. Now I'm going to click here, and if I didn't, what would happen is it would also display all of these other summary statistics, and then the output looks really busy, and I don't want that. Okay, I want a nice, clean, simple output. So this way you only get one value, and you type compute, and as advertised, that's your output. So let's think a little bit about what that means. So we found out that $1 million was a 90th percentile. So if this is a histogram, and it is, of those salaries, we see strongly right skewed. The mean, which is that green line, is pulled out towards the tail. Okay, so all of this is kind of hanging together mentally for you now. And if we find $1 million, to say that it's in the 90th percentile means that 90% of the players, or 90% of the values, are less than $1 million. And only 10% of the players made more than $1 million. Now, a little word of warning. The book uses a particular notation. So to represent the value of the 90th percentile, they use P sub 90 for 90th percentile. So for example, the way that you would express that in this problem is that the 90th percentile is $1 million, and that's how you would write that. Okay, so for our reading quiz, the first question, I want you to use this data set and go through the same mechanics, the same process that we went through to find the 20th percent of the salaries, 20th percentile of the salaries. And think about how you would interpret that value. Okay, so now we know how to compute percentiles from data. What if we have a population distribution? We no longer have sample data. And before we get into this problem, I want to talk a little bit about distributions first. So one way of thinking about a distribution is that it's the histogram of the values of a variable if we had every single value in the population. And a distribution itself, it tells us what values the variable can take on in the population and how likely it is to take on those values. So we tend to think about, plots of distributions as that nice, smooth curve that we're trying to fit our sample data that we make a histogram to. And we're thinking that's what the values in the population would look like if we had the whole population. And of course, again, samples approximate populations. So we're thinking that that histogram we get using the sample data approximates that distribution that we would get if we had all the values in the population. So the idea is that, you take the data, we're only going to look at the quantitative variables here, you plot the histogram, and you can see that smooth curve that seems to evenly cut through the data. And that's what we think the population distribution is. And so we can see that the distribution here tells us that diastolic blood pressures, which is what we're plotting here, and this is from over 1,000 Swedish men, they basically take on values from about 50 to maybe 130, okay? And the shape of the distribution in the population seems to have a bell-shaped like curve. And it turns out that even though not all data is bell-shaped, we know that financial distribution, which is very important in this class, generally tends to be right skewed. It's going to turn out that that bell-shaped curve plays a central role in statistics. It's very important. And it actually has a special name. We call it a normal distribution. So what does normal mean? Well, here's an abnormal distribution. Okay. Here's a paranormal distribution. And here's a normal distribution. I know, bad statistics jokes. Okay, so the normal distribution is a lot like other distributions, okay? It has this bell-shaped curve. It's unimodal, it's symmetric. The mean is equal to the median, okay? So we know how to describe it really well. And of course, we use the standard deviation, which is what we're going to use. And the normal distribution models a lot of different populations. So if you look at stock returns tend to have a normal distribution. When you look at deviations from manufacturers' claims, if you look at, for example, the weight of stuffing in an Oreo and you take a gazillion Oreos, and people actually do this later on, we're going to talk about a famous study to see if double stuffed Oreos are really double stuffed. Someone actually did this in real life. What you'd see is that it's not going to be exactly what the manufacturers claim, which is going to be at the mean. It's going to have a kind of, the deviations are kind of be scattered about the mean in a sort of bell-shaped curve. Physiological measurements, blood pressure, heights, lengths of specific body parts tend to have a normal distribution. And standardized test scores also have a normal distribution. And this is a really good example to talk about because you have to realize that nothing in real life actually has a normal distribution. The normal distribution just models data. So if you look at IQ, for example, okay, if the IQ really had a normal distribution, and by the way, these little, this outline here, the jaggedy outline, that's actually a histogram of a gazillion IQ scores, okay? And you can see the normal distribution fits through it really well. But technically, the normal distribution goes from minus infinity to positive infinity. Well, have you ever met anyone with a negative IQ? I know there are a few people you kind of wonder about, right? Like, the people that aren't playing with a full deck, they might have a negative IQ. But in reality, we know people can't have negative IQs. So this, in a sense, is a lie. However, it's a very useful lie. It turns out that the normal distribution is such a good approximation that we can use it in real life and get really good results. And so there's a famous saying by a statistician, George Box. He said, all models are wrong, but some are useful. And it turns out that the normal distribution is incredibly useful. And we're going to find out that actually there are certain things that come incredibly close to a normal distribution. So we're going to talk about that later. So it's very, very useful for us. Now, normal distribution is very simple to describe. There's only two things that we need to know. There are two numbers that once you tell me something has a normal distribution, completely, define that particular distribution. And they are the center and the spread of the normal distribution, which we know is going to be given by the mean and the standard deviation because it's symmetric. And so if you look at a normal distribution, these two parameters completely define or uniquely identify a specific normal distribution. The mean is denoted by this symbol mu. It looks like a U with a tail on the left. And that's the Greek letter for lowercase m. And the standard deviation is given by this thing that looks like a sideways 6. It's called a sigma. This is going to stand for the population standard deviation. Okay, so let's go ahead and try and test our knowledge. So here we have three normal distributions. Where are they centered? Well, the means are all at 0. The mean tells us where the center is, right? But these three numbers, let's see, sigma is equal to 2. That's telling me the width is characterized by 2. This width is 4, and this width is characterized by a length of 8. And so, of course, the bigger the standard deviation is, the wider, the fatter the curve is, right? So the thinnest curve is going to be this top curve right here. This is characterized as having a standard deviation of 2. And the second curve is going to be a little wider because its standard deviation is larger. And then finally, this last curve is the widest, so it has the largest standard deviation. Okay, so for your reading quiz, what I want you to do is match these four normal distributions. This is A, B, C, and D to their parameters. So we said we were going to be computing percentiles with population distributions, but we haven't done that yet. Well, here's how that's going to work. So what if I ask you, what is the probability of finding a person 6 feet tall? And the answer is 0. And you might say, oh, that's ridiculous. I know a lot of people are 6 feet tall. And the answer is no, you don't. Because what we're thinking of when we make that statement is a person is exactly 72.0000000 inches. And of course, nobody is. And so this points out a really important fact when we're talking about probabilities and we have continuous distributions, right? The values fill up an interval completely. What this tells us is if we have a continuous random variable, and I'm going to use RV for random variables sometimes, like, for example, height of a person, right? Or salary of a baseball player. The probability that that variable takes on a specific value is 0. So how do we compute probabilities when we have continuous random variables? And the answer is percentiles. Okay, so this next slide is really important. I want you to listen very carefully because there's 3 facts that we need to know to be able to work with distributions and compute percentiles from them. So the first fact is that when we're given these probability distributions, the area under the whole curve is 1. The second really important fact is that probabilities are actually areas under the curve. So if I want to ask the question, what is the probability that a randomly chosen value from the population is between 2 values, A and B, what I'm going to do is sketch out that distribution, that curve, and the area under the curve between A and B is the probability. So this area between A and B under the curve is the probability that I'm going to find a randomly chosen value between A and B. Now, we're interested in special probabilities. We're interested in percentiles. And percentiles aren't just areas. They're areas in the tail of a value. So for example, if I pick some randomly chosen value x, so x is just some value, I'm not going to say what it is, but it's a specific value. The percentile of x is the area in the left-hand tail of x. So this area here is the percentile of x. And isn't that what we saw when we looked at the income data? I mean, even though we didn't make a big deal about it, how did we get the percentile? Well, we could have got the percentile by adding up all of those percentages of the bars, right? And that was from sample data. So we're just really adding up the areas of those bars. And it turns out that we're basically adding up the area under the curve for the probability distribution for a population. So if you go back and you look at this data for the SOB, and we're going to work with this in a second, if I plot this data, this is data taken on a bunch of used SOBs back in 2013. I collected this from Auto Trader. Okay, when you make a histogram of those prices, you see that it looks somewhat like a normal distribution. And in fact, you can actually use StatCrunch to overlay the best fit normal distribution. And you can see it's not too bad. So let's do some calculations with this distribution, assuming the mean is roughly 29,500 and the standard deviation is roughly 3,500. Let's assume that this data estimates this curve well enough that these are the values for the actual population. Okay, so let's go ahead and compute probabilities as percentiles. We're going to model the population SOB prices now as having a normal distribution, and this is the mean, and this is the standard deviation. And what I want to do is I want to ask the question, how likely is it I could get a randomly chosen SOB that costs $31,000? Now, super important, the term how likely in statistics is code word for percentile. And you might want to write that down. That's such an important point. How likely means percentile. And because we're going to use that fact over and over again. And so if I go ahead and I look at the SOB prices, right? This is my center, the mean. This is the SOB price I'm interested in. And how likely I could get a randomly chosen SOB whose price is $31,000 is asking for the percentile, which for a value above the mean is the area in its right-hand tail. So I'm going to be computing the upper percentile here. And this upper percentile is going to tell me how likely it is that I get this value. Okay, so let's see how this works in StatCrunch. We're going to now use a feature we haven't come across yet. We're going to go into the normal calculator. And we're going to go to stat, but instead of summary stats, we're going to go ahead and click on the tab above it, calculator, and we're going to choose normal. And this is going to let us do calculations with a normal distribution really easily. So the first thing we're going to do, when we click on this, a window will open up. We're going to type the mean and the standard deviation in. So I'm going to go ahead and put my mean of 29,500 without a comma in the box next to the mean. And I'm going to fill in the field next to standard deviation with 3,500. And let's go ahead and answer our question, how likely is it that we could get a randomly chosen value less than 31,000? And so I've entered everything I need. And what I'm going to do now is I'm going to enter 31,000 right here. I want to know what is the probability of a randomly chosen value of my variable being less than 31,000. And let's see what we get. We should get roughly 66%. So let me step through this with you in StatCrunch. So this is the SOB data here. And I'm going to go to Stat, Calculator, Normal. And I'm going to enter in my mean. So the first thing StatCrunch does is, okay, you want to work with a normal distribution. Tell me which one. Well, what are the two pieces of information I need to uniquely identify a specific normal distribution? Well, the mean, which is 29,500, and the standard deviation. And now I'm going to go ahead and put the price that I want the percentile of. And so I can go ahead and I can compute the lower tail or the upper tail. Okay, in this case, I'm going to compute the percentile first, and we're going to see that's roughly 66%. But remember how likely for a value above the mean really means upper percentile. So I'm going to change this less than to greater than, and I'm going to get 33%. So this tells me that the value, 31,000, is in the upper 33rd percentile. Okay, good. And that's all you have to do to use StatCrunch to go ahead and do calculations with a normal distribution. Okay, change it, I get that. Now, sometimes we want to calculate the probability that we get a randomly chosen value between two values. So what if I want to know what is the probability that I get a value, say, between 28,000 and 31, I'm sorry, 28,000 and 31,000. All right. What I'm going to do here is I'm going to go ahead and click on that between tab. And then we're going to go ahead and enter our parameters like normal, which we've already done. And then we're just going to put in the two values that we want to find the probability that we're between those two values. And let me go ahead and do that. So I'm going to go back to StatCrunch here. And all I'm going to do differently is I'm going to click between. And we wanted the probability that we were between 28,000 and 31,000. So I'm going to put those as the upper and lower limits. And we click on that. And we see that it's roughly 33%. Okay, good. Now, we might want to ask another question. Sometimes we want to go backwards. Sometimes we are given the percentile and we want to know the value corresponding to it. So I could ask the question, what value is the 90th percentile? And here, all we're going to do is use exactly the same, the same GUI here that we've been using, right? And now we're just going to enter 0.9 here. Okay, so I'm going to use the same normal calculator, and I'm just going to change the probability, and it's going to give me the value. And notice one of the really cool things about StatCrunch is it's shading the area corresponding to the probability. So this area is 90% of the area under the curve. Just like if we go back, this area here was actually 33% of the area under the curve. It's actually a really nice feature about StatCrunch. So let's go ahead and do that. So if we go to StatCrunch here, and now I'm just going to go back and click on standard again, right? And I enter 0.9. Okay. Now I have to change this. I had greater than, I have to change it to less than. And notice one of the really nice things about StatCrunch is it tells you when you make an error. Okay, I knew that I made an error there because the area was really weird. I knew that 90% should be shaded, right? And so here we see that the 90th percentile is roughly 34,000. It's $33,985.43 to be precise. Okay. So this is how we do calculations computing percentiles with probability distributions using StatCrunch. Okay, so let's go ahead and try out the reading quiz now. So the reading quiz, we're told that we know the systolic blood pressures have a mean of 124 and a standard deviation of 16. And so we can assume a normal distribution because we're looking at a physiological measurement, okay? So using that normal distribution calculator that we just were working with, I want you to find the 90th percentile for the blood pressure readings. And then go ahead and find out what percentage or what proportion of the population has a blood pressure between 103 and 140. So you can take a few minutes, go ahead and do that. Okay, so that's all for this lecture. Hopefully you find that computing percentiles using StatCrunch is really simple. And in the next lecture, we're going to talk about another measure of relative standing called the z-score.